Please take your seats. So today our speaker is Dorottya Szécsi. She did her PhD at Bonn University in 2016. Then she had a bunch of postdocs at Astronomical-Institut, Czech Academy of Sciences, University of Birmingham, University of Cologne, and now she's at Nicolaus Copernicus since 2021. She's the leader of the Eötvös grant, also got PhD last month.
Habilitation.
Sorry, habilitation, yes. And we now see slightly different view over here. What happened here?
I changed
View.
yeah, I know what I did. Exactly. Yeah. Sorry.
And the presentation will be about massive stars.
Yes, exactly. Thank you very much.
Go ahead.
Hi, everyone. Thank you very much for the introduction. I did not expect that, so I prepared a slide about myself, but I can just skip that now, I guess. So, as you just heard, I'm an assistant professor in Torun at the Nicolaus Copernicus University, and I'm working on stellar evolution, massive stars, low metallicity environments, all that jazz. And today I want to share some dirty secrets with you, because I'm pretty sure you have heard some of it already, but maybe not. So let's see how much you know about it. Okay. It is a truth universally acknowledged that many people use stellar evolutionary models in their research. Maybe even you. Hands up, who has ever used stellar evolution models? Mesa, this guy. Wow. Okay, so you're my audience. Excellent. So in this talk, I'm only going to talk about massive stars. I'm not touching the topic of low mass stars, and don't ask me about it because I'm not an expert, and there are problems there as well, but you should talk to another person, not me. What I want to tell you about is massive stars, meaning more massive than 8 solar mass, and particularly those libraries and grids, or sometimes they are called grids or libraries, like the Geneva models or the Bonn models, or you can even do it yourself with Mesa these days. And these tracks, of course, as you know, have a wide range of usage. You can, these are just a few examples. You can try to obtain mass and age of observed stars using these stellar evolution models. You can apply them in star formation simulations, star cluster formation studies to predict what happens with stars that are forming near to these massive stars. You can model the chemical evolution of the universe using these tracks, and this is my angle, actually. You can apply them in binary population synthesis to predict various things, but gravitational wave event rates amongst others. So what do you do? Please tell me, what did you use stellar evolution models for? Yeah, thank you. The others? Do we have any PhD students in the room? You're the PhD student? Okay. What did you use stellar evolution for? If you have.
Binary systems.
Binary systems. Did you evolve massive stars or low mass stars?
Both.
Both? Okay, very good. The others? What about you?
Yeah, low mass stars.
Low mass stars, only low mass stars. Okay. Anyone else wants to share what they did with stellar tracks? I'm very happy to chat with all of you after this talk, so you can just contact me and we can reach about massive stars. Okay, so necessarily, unless you're a stellar evolution expert, unless you are actually someone who did a PhD or a postdoc in that field, then necessarily the models are most of the time used as a black box. if you just download MESA, but you never learn what's in there, that will be a black box for you. You can push the button, you get out some kind of results, some kind of data set that you can use in your own research, but unless you really investigate what's inside the black box, that's it, you don't know, which is fine. I'm not saying everyone should be a stellar evolution expert. I'm not saying that. I realize that you're an expert in your own field because you are an expert in that, not me. I'm the expert of this. So this is why I'm here today, to tell you about the black box. So let's peek into the box. Let's see what's inside. So basically what I'm presenting today is mostly built on this paper from 2 years ago, led by my then PhD student, now postdoc. But there are, of course, other works that deal with similar issues, so you can check out those other papers too. But my talk is mostly based on Argelander et al. 2022. So in that paper, what we did, we compared 5 sets of stellar evolutionary models from 5 independent projects of codes, so that you don't have to do it, right? We just went online, downloaded the libraries, and put them next to each other to see if they predict the same thing. If they don't predict the same thing, just to see. The libraries we investigated were the Padova code, so Parsec, MESA-based library called MIST, the Geneva code, Bypass, which is another famous stellar evolution developed by people in New Zealand, and the last one is the Boost project, which is basically Bonn-Cologne. That's my own minor project, basically. So we've done with these 5 sets of stellar evolution tracks and compared them. Let's see. Important caveat, so you cannot read that, I guess. I'm so sorry about the. This is a
Models
very
with the same mass and
okay. The box said only comparing models with the same mass and composition and single stars with no rotation or slow rotation. So basically, very basic stuff. Same mass, solar composition, and single stars. We are not even touching more complicated things than rotating models or binaries or nothing, just single stars. So this is what we got. This is a stellar evolution of a 25 solar mass star. So this is a massive star, an O star. At least during the main sequence, it's an O star. I can do this. So yeah, this is classic stellar evolution for you. O star phase, Hedgehog gap, and then red supergiant phase. For the same 25 solar mass star from the 5 different codes. Now what you can see here is that the situation is not that bad, right? I mean there are some discrepancies here around the end of the main sequence. Sure, the red supergiant phase is differently predicted, but more or less all 5 simulations predict the same thing, which is just good news, right? Yeah, but then we went on to compare other models, and the situation is not that beautiful anymore. This is the same thing here, right? So this one here is 40 solar mass. So we are increasing the mass. This one is 40.
sorry, you can use pointer on the computer so that people over the internet on your computer, if you just move the mouse, yeah, other people will see that.
So yeah, so this is the 25 solar mass case we just discussed. Fine. This is 40, and you can see that already here the situation is getting muddy. The tracks diverge quite a lot, especially at later phases. Some predict Wolf-Rayet stars here, like very Wolf-Rayet stars. Some don't. And then, the situation gets even worse when we go up to 80. So this is 80. This is a very massive star, 80 solar mass, and this is 120. And in those very massive cases, the tracks are just all over the place. And when I first saw this, I was honestly scared because, I know how people use stellar evolution. I know it's just a black box for you. So you will go there, download one of these tracks without ever double checking them against the other tracks. And just download them and apply in your own research and suppose that we understand these tracks, but don't. Like if there is no consensus amongst massive star experts because they all produce different predictions, then you should probably not just rely on one single library for your own research, right? Because it's yeah, that's the situation. We also went on to compare other quantities, other stellar properties. For example, here I'm showing you on the right-hand side. I'm showing you the same 5 sets of tracks, but here the x-axis shows the initial mass and the y-axis shows the final mass. And you can see that the libraries again predict many different things when it comes to the final mass of the star, which is scary because if you want to do gravitational wave event wave predictions or whatever else, right, like binaries or anything, yeah, you can get a result. You can get a completely different result based on which that library you use. The left-hand side, you see the same x-axis. So again, the zero is mean sequence mass, the initial mass of the star, and the radius. This is useful for binaries. So if you want to run binary populations, this is a useful figure because the radius basically can be translated to the Roche size. Yeah. Say things about binaries. So okay, this is the situation. This is scary, but this is very interesting because in the paper we also wanted to tell the community about why this happens, not just present that this happens, but also explain it. And I have a quick and dirty answer and a long and complicated answer for you. The quick and dirty answer is that we just simply don't understand massive star physics that well yet. So just to give you an idea, this is a homogeneous survey of massive stars in the Large Magellan Cloud in one of the large star-forming regions there. And as you can see, we have quite many observations at lower masses, right? Like 10, 15, 20. We have, you know, a nice statistical sample of observations. This is why the 25 solar mass case that I showed you was that nicely matching between the 5 simulations, right? Because we have data to constrain the models with. However, when we go to higher masses, 30, 40, 60, see what happens? That we don't have observations anymore. We have a handful, but definitely not enough to constrain every single parameter, every tweak in the code that we need to constrain, that we need to calibrate. So basically, this is the short and dirty answer that we don't have enough observations. We need more observations of massive stars at all metallicity, not just solar, Large Magellanic Cloud metallicity, SMC, Small Magellanic Cloud metallicity, even lower than that, dwarf galaxies, all these places, early universe, and a variety of stars, not just single stars, of course, but binaries too. And those observations are extensive. Massive stars are mostly emitting radiation in the UV, so we need Hubble or other like strong UV telescopes, and you know, it's just difficult to observe many of them. So yeah, and they matter, these very massive stars, because you could say that, well, who cares about those very massive stars? They are rare. Why should we care? But they matter because the higher the mass, the higher the stellar wind strength. So the more mass a massive star ejects during its life, therefore, the more it contributes to its surroundings. It changes the chemical composition of its surroundings, the chemical evolution of the galaxy. If you want to understand that, we need to understand those massive stars. And those are the stars that are responsible for forming the most massive black holes that we observe with LIGO these days. And we just don't understand their evolution yet. So how do we expect to understand those black holes, right? So they are very important. We cannot just exclude them from our research. All right, that was my short answer. What about my long and complicated answer? Let's see. Are you curious about hearing the long and complicated answer? Let's see. We have to start a bit earlier. What is a star? Tell me, what is a star?
Oh, heavy generic.
That's completely correct.
It's something that is not rotating so that it fits your models.
I can actually do rotating models. It's not a big deal. There are ways how to do that. We tweak the code and we can do rotating models. For me, a star is basically a sphere of gas isolated in outer space. It's basically a hot dense sphere of plasma. And it's held together by, of course, its self-gravity and the pressure gradient acting against the gravity. So these two forces lead to this long connectivity. Where is its surface? Maybe I have the students. Where is the star's surface? How do you define? Because there is no box containing this, right? It's just a sphere of gas out there, but there is no container. How do you define where the plasma ends? Good. Yes, that's a problem. Photosphere. Very good. That's what I wrote there. The photosphere. That's where the photons escape. Of course, it's not completely trivial how to define the photosphere because that place is also depends on the opacity. But like an easy answer is the photosphere because this is what we observe. This is what we see at the last, right? This is where the photons arrive to us. So, okay, next question. What is inside? How do we know what's inside? Yeah, but the spectra tells you something about the surface, not about the photons. So how do we know what's inside?
Dynamical equilibrium and this thermal equilibrium and so on, and you integrate that.
Yeah, exactly. I'm calling this, what you just said, the theoretical modeling of the stellar structure. This is exactly what you just said. So basically, we have a set of partial differential equations that describe this sphere of gas in equilibrium, in hydrostatic and thermodynamic equilibrium. And basically, these four equations describe very simple physical principles. The first is mass conservation, the second is momentum conservation, the third is the energy conservation, and the fourth is some kind of transport of energy. We have, of course, extra additional equations that we need to include into this set of equations, but this is the basics of stellar evolution. We also need to include sorry, what is it? Radiation transport is included into the fourth equation actually, via this weird nabla symbol, which is not a nabla. So it's included. Convection, yes, that's something we need to include. We also need to include extra things like overshooting, convective overshooting, all these things. Opacities, yes, lots of other things. But these four equations constitute the basis of what we do. And there is a fifth equation, which is again not one equation, but a lot of equations, with which we include the composition change and therefore the time, right? So the first four equations, actually, there is no time in this, actually. So this is just the structure of a star at a given time, a snapshot of the star's life. If you want to include the whole evolution, the whole lifetime, then we need to include the composition change due to nuclear burning, because that defines the time step. That basically defines how the star is. It's like from birth via these snapshots until death. So basically, we solve the first four equations, then change the composition. Then solve the first four equations again in the next step, change the composition again. Then solve the first four equations and change it, and so on and so on and so on, from birth to death. This is stellar evolution. This is how we got all those lines. Can you see the lines underneath? So of course the dots are observational data, but the lines underneath are models. And they were computed using this strategy. And this strategy is, of course, very, very old. People have done this already in the 60s on those huge computers, which were as large as this whole building. So yeah, this is old stuff, but the most modern codes that we have, they can include rotation, as I said, they can work with binary stars, they can do a lot of things. So, do you remember when I said that stars are held together by their self-gravity and some kind of pressure, internal pressure, right? And it leads to this long-term equilibrium. Now, there is a very important term for us to learn today, the so-called Eddington limit, which is basically where this equilibrium is compromised. There are other ways how this equilibrium can be compromised. I think I have a slide about other ways. Yeah, there are other reasons for falling out of equilibrium, but getting close to the Eddington limit is one of these possible reasons. What is this Eddington? Basically, what we have is gravity acting inwards, and we have the force of radiation acting outwards. And normally this does not. So basically, we have internal pressure acting against gravity, but in very massive stars, radiation pressure overcomes internal pressure, right? Because those stars are very luminous. They are on the top of their Hertzsprung diagram, so they produce a lot of photons. Radiation pressure becomes more important than gas pressure. And when this is the case, it can overcome gravity. And this is what we say, this is what we call the Eddington limit. And when a star comes or reaches the Eddington limit, it means that the radiation becomes stronger and it wants to disrupt the star. Does that make sense? There are all those definitions that you don't need to do with that. Which is basically this concept. So what is the consequence of reaching the Eddington limit? And I'm talking about this because this will be the reason why we see all those variability between the stellar tracks that I started my talk with. So the consequences of approaching the Eddington limit for the stellar interior is that we get so-called density and pressure inversion in the envelope, which is basically this thing here that you can see. Can you see this peak here? What is, so this diagram is the, see the stellar radius in the x-axis and the internal density on the y-axis. This is basically the structure of your star. This is the core here, and this is the envelope. And normally, under normal circumstances, when there is no Eddington limit, nothing, just normal star, the density is a constantly dropping function of the radius. But when a star is close to the Eddington limit, then these kind of things can develop. This is the so-called density inversion. So we have this peak near the surface in the density. And this is because basically the photons want to escape, but the structure cannot accommodate them anymore. They cannot escape, they are trapped. And they cause these weird numerical situations here. At least in one-dimensional stellar evolution. Because all this is 1D, of course, as you know. There is not many ways of dealing with this in 1D. 1D codes do this, unless we do something. So basically, there is no efficient transport mechanism to transport the energy away that needs to leave the star, and therefore the codes do these tricks. They try to adjust and do this. Also, another thing that you may hear in the literature or read in the literature is the so-called envelope inflation, which basically means this. and you see this long, straight horizontal line here. This is the envelope. So the radius basically is increased while the density is really small. So this is a very dilute, large envelope. It's so-called inflated envelope. And this whole situation is numerically challenging for the codes. So usually when this happens, the codes just crash. And then you cannot continue the evolution of your structure. If it happens during the main sequence, if it happens during whenever the codes crash, you cannot continue the evolution unless you do something. And this is where, going back to the original question, so how do these codes deal with this Eddington limit of proximity and this inflated envelopes and density inversion and stuff? So basically, every code does their own pragmatical solutions. So for example, in the Parsec code, they are artificially limiting the temperature gradient, which is a pragmatic solution. In Mesa, there are various possibilities, but at least in this MIST project, they apply the so-called NLP plus formalism, which is, you don't want to go into that, which is basically limiting the super-radial velocity. Never mind, it's again, it's basically changing how convection is treated, basically changing how the transport of energy is treated in the code, which is again a pragmatic solution that people apply just to push the models forward, just to overcome this numerical. In the Geneva and bypass models, they apply an artificially enhanced mass loss rate at the right moment. The reasoning behind it is that, well, the star is pushing its envelope away anyway, so let's just have and remove artificially the top layers. Problem is that if you remove the top layers, you remove these inverted layers, they develop again. So it doesn't really solve the situation. They just develop again, and you need to remove them again and again. You know, it gets tricky. And it's pragmatic. There is not really observational evidence for doing that. I mean, we do have LBB stars, which have very strong episodic mass loss rates, sure, but not all stars are LBBs, and we don't know if these stars are LBBs. Anyway, this is another solution that people apply. And in my own project, I developed another pragmatic solution again. So I'm not saying mine is good. I'm not saying I know what to do. I also don't know what to do. But I apply another solution. I basically let the envelope inflate as long as it takes, as long as I can. And then in post-processing, I apply a normal mass loss rate and remove layers and layers and layers from that model. Again, it's a pragmatic solution. I'm not saying it's a good one. I'm just saying it's a good type. And yeah, and this is what explains the problem. This is what explains all these variability that we see, because the codes basically apply various pragmatic solutions without not much observational or any kind of support, I would say. Yeah, and this is why we don't have a consensus. Okay, so in the same paper, we again also wanted to predict some other quantities just for the community to see. So we compared ionizing flux, because ionizing flux of transit stars is a very important quantity for star formation people. And so we just created very basic population models and predicted how much ionizing photons they emit, based on the 5 libraries, and we found that there is about 20% difference between the smallest and the largest amount of photons, which is yeah, that's the number we got. And again, because we wanted to make predictions or wanted to contribute to gravitational wave research, we also computed the mass of the black holes and neutron stars that these models predict. And we found that there is you can get up to 20 solar mass difference in the mass of your black hole. Basically here, and you see the lowest and the highest differs with 20 solar mass. So this is quite scary. 20 solar mass is It's a lot. Yeah. What to do now? Because this is a problem, we understand where it comes from, how to solve it. Honestly, I don't really know. However, I recently started to talk to people in my own community about this. We all know the problem, right? Like this paper was aimed at a general audience, not my own community. Of course, my people know that for decades. And we are working on it. Many people in my community are working on it, but the problem is difficult. So recently, I reached out to some colleagues who do 2D modeling of those surface regions, of those problematic surface regions where these density inversions develop. And they seem to find from their 2D simulations some kind of solution. So they seem to see what happens there actually, quote unquote, reality, at least in the reality of their 2D simulations, and we might have a solution soonish. So right now we are trying to implement their treatment into MESA. I don't know when that's going to be done because it's a huge project, but maybe it's a solution for the future. Maybe in a few years' time we are going to have a working solution that would end up in consensus or the tracks doing the same thing, hopefully. But until then, I want you to remember that first, Eddington limit is a thing. Second, that stellar evolution above 40 solar mass has not yet reached consensus. Not even at solar composition, and I didn't even touch lower metallicities. We could talk about dwarf galaxies and early universe and all these environments where massive stars form with lower metallicities than solar. And we don't really know anything about, like, we do know a lot about those stars. But like we know even less about those stars than we know about solar composition masses. So yeah, stay tuned. Please use any stellar models with extra caution about this mass. And very important, be flexible for updates. Updates are coming. I'm telling you, the community is working on it. We know the problem exists. We are trying to figure it out. But until we do, please be patient and please be flexible. So whenever updates happen, be open to update your own code and your own projects with the new stellar tracks. Also, what you can do is you can, instead of just downloading one library and using it forever, you can download several libraries and compare their results, because we really don't know which one is correct. So the best you can do is to treat all of them as a possibility and compare their results in your own project. Right? And yeah, so my last point is, if you decide to do it yourself in MESA, which is fine, sure, do it. But please ask an expert. Ask someone like me, not necessarily me, but ask someone from my community before publishing. Because honestly, I'm not going to quote names and papers that I have seen. I have seen papers published with using MESA stellar evolution tracks used as a black box. And I just look at the figures and I can see it's not correct. Like they didn't know what they were doing. And this got published, this got accepted, and people are citing those results while they are just, like, don't do that. Please ask a stellar evolution expert before you publish anything with your black box MESA. That's my most important message today, I guess. And even better, hire one. If you have money, you can just do a job call for a stellar evolution expert and employ them in your group, and they will be more than happy to explain things to you and with this or any other okay, my last slide is a bit of personal touch. So I want to introduce you to my people, my research group. She's Poojan Agrawal. She was the one responsible for the paper that I just presented. So I don't want to take her credit. Credit is for her. She was the leading author, and she's a brilliant postdoc working in the US right now. And yeah, she did all this research. Please check out her other papers too, because she's writing excellent papers. And this is my research group in Torun. You might recognize the background over there. So that's the cathedral in Torun, and before it, it's my PhD student Dorottya Szécsi. We have my other PhD student Hanno Stinshoff, my postdoc Kosik Sen, and at the self-advertisement, I'm going to hire this fall. I'm going to have a postdoc opening. So if you're looking for a postdoc position or know someone who's looking for a postdoc position, please keep in mind that I'm going to have an opening sometimes around October, probably, depending on the university bureaucracy. But I try my best to have the call out in October, and yeah, I'm going to look for people to work with. And with this, thank you very much, and please ask any questions.
Thank you for a brief presentation. Now we have time for questions.
So, apart from delivering stars, which have some limitations because it's difficult to ascertain their state, do you think that there is a way out by looking at the observations of gravitational wave sources and looking at the mass spectra of black holes, and that they can constrain what we don't know universally?
Oh, that's a very good point. It would be awesome to do that. I would love to do that, but I think there are just too many open parameters in stellar evolution, especially binary evolution. So yeah, in binary physics, there are so many things we really don't know, and then the population results depend on that. So when we want to match the black hole mass distribution, we can do it by tweaking the parameters. So it's hard to exclude any of these models based on that. Yeah, there are too many open parameters we can tweak apart from this.
So I'm guessing the most information you can get for the stars that are in open clusters.
Mm-hmm.
So what is the most massive star that we know in an open cluster?
Oh, that's a good question. So the most massive star we know about is in the LMC, in this certain evolution, the same place that I showed you, and it's something around 250 solar mass, depending on who you ask. But that's the highest that has been claimed so far.
And in our galaxy, in open clusters of our galaxy?
That one I don't know. That one I would need to look at. Probably something around 120, 150 perhaps. Something that I would need to look at. I don't know by heart.
And the highest mass star in a binary stellar system is probably like 80 still?
Yeah. Binary, we don't really go up.
Any other questions, Martin?
You have mentioned that there are 2D models of surface layers of stars. There is no possibility to make a 3D because there have been models several years ago, even since 2000, 3D radiative heat models of outer layers of convection zones,
Yes.
like Nordlund and so on.
Yes.
So there are no projects like this.
The problem is the time scale. So 3D models, of course, are very expensive, and the time scale that we need to deal with here is like several 10 to the 4 years, 10 to the 5 years, and those simulations that can resolve convective turbulences and stuff, those are like, second time scale, like really short time scale compared to several orders of magnitude different from what we need here. But that's the problem. It would be really expensive and would take forever to run a 3D simulation.
Make some snapshots. some kind of situation.
Mhm.
This initial model, you put it there's some kind of equilibrium, maybe not, and you, let's say, left it and you choose another model, the other, let's say, stage revolution.
Yeah, but until this feature develops or doesn't develop, you would need to wait a long time, and that's expensive.
Any other questions? Yeah.
So, is the density information show written physical evidence of it?
Physical
Or
evidence.
observational evidence?
No, not, we do have physical evidence for inflated stars, yes. We can actually peek into the layers below the surface because we don't see them. But there are observations that can be only explained by supposing this effect. Is that what you meant, or? I mean, we cannot directly see the layers below the surface.
Will it be clearly known in the mass transfer variables? That means
So
will the density question can it be known in mass transfer?
these were models for single stars.
No, in binary.
What do you mean? I'm not sure I'm getting what you want to say.
So if the density question is in physical, will it play a role in mass transfer in binary systems?
I don't think it would make a difference. And it would, because then if your envelope is inflated, which is a consequence of this situation, then you would reach the Rochlov earlier. So you would have an earlier Rochlov overflow, and the mass transfer would start earlier. So that would be the most important consequence, I think. Thank you.
Łukasz, do you have a question?
Well, I just wanted to ask, first I wanted to say thank you for this very inspiring seminar. And I wanted to ask, do you have any expectations towards Gaia DR4 coming in soon, which is going to, find, well, there's going to be a lot of products, and one of them is going to be binaries, where with astrometry people will be able to measure masses. So how is it going to be a gold mine, or are you going to dig into this data set yourself, or are you just going to wait for the results with your group?
I personally not planning on digging into Gaia data at this point, but yeah, I'm very excited to see what people find in that. Yes, it's actually very exciting. Yeah.
Cool.
Okay. Thank you very much then. Thanks for a very nice seminar once more.